Hey everybody, this topic is about conservative and non-conservative forces, and this section is a little earlier in the book, but I'm saving it here for kind of the end of the chapter because some of you may not have seen the math required to discuss this topic. So because of those kind of steeper prerequisites, I feel like it's not fair to ask this on an exam. So you won't see this on an exam this semester, but it's definitely something you need to know for future semesters. Okay, so hopefully it's not so bad. I'll walk through all of the math. So let's say you're given some forces. Like, say this example, we have these three forces. I'll just call them F1, F2, F3. These three forces. How do you know if they're conservative or non-conservative? And there's a test. And the test is you take the curl of whatever that force vector is. If the curl is 0, then that force is conservative. If the curl is not 0, then the force is non-conservative. That's all. Okay, so my concern is that some of you may not have seen the curl in calculus class yet, so let me explain. Another way to write the curl is del cross F, and I will just write it out, like doing a cross product. I, J, K, and we're doing this example in Cartesian coordinates. There are other coordinate systems that we'll discuss in future semesters. Okay, and then this operator is just partial derivatives. Okay, so this is the partial in the x direction, partial in the y direction, partial in the z direction. And then this vector goes here, decomposed. Okay, so we basically just do this cross product. We evaluate this determinant. So in the I direction, this fish right here, this times this minus this times this. So in the I direction, d by dy of fz minus d by dz of fx. Okay, and then in the j direction, minus j, and then this times this minus this times this. So d by dx of fz minus d by dz of fx. Okay, and then in the k direction here, this times this minus this times this. K direction, so d by dx of fy minus d by dy of fx. Okay, so that's it. That's how you do the curl. And then if this equals 0 vector means 0i, 0j, 0k. In other words, this is 0, and this is 0, and this is 0. Okay, and then let's say this is in the xy plane, and there are no z, like variables. So there's just x and y, no z. So then there's nothing here, and then there's no fz, so this is gone, and this is gone. So all that we're left with is this right here equals 0. And then that's exactly what is in the book. So it is mentioned in the book, but without really an explanation, just this here. Okay. Let's try it. So let's try it here. So given this force, axy cubed plus ay x cubed. If we do this curl, I mean, there is no z variable anywhere. So indeed, this is gone and this is gone. So really, we're just checking this one right here. So here, the partial of x of the y component. So this is the y component of the force vector, right? And we're just taking the partial derivative with respect to x. So we're doing this. AYX cubed. Okay, and then partial derivative means a and y, we just consider them as constants. The only variable that we're considering is x. Okay, so we treat a and y as constants and then take the derivative of x cubed with respect to x. So that's 3x squared. Okay, now we check the partial of fx with respect to y, like this over here. Okay, so partial with respect to y of, here's the x component right here, axy cubed. Okay, so with respect to y, both a and x we treat as constants, and then just take the derivative of y cubed with respect to y, so that's 3y squared. And now this is not equal to this, so that means this force is not conservative. Okay, let's try this one over here, the next one. Y squared over xi plus 2y log x over b, j. Okay, so let's check the partial, this one first. So the y component is right here. And take the derivative of that with respect to x. So in other words, we treat 2 and y as a constant. And so then just take the derivative of log x over b. So just take the derivative of ln x over b. You could write ln x over b as ln of x minus ln of b. And then when you take the derivative of this, right, the derivative of log x is 1 over x. The derivative of a constant is 0. So it's just 1 over x. Okay, now let's take the other one, this one, the partial of the x component with respect to y. So right here, so we treat 1 over x as a constant, and then just take the derivative of y squared, which is 2y. Okay, so this is 2y over x, this is 2y over x. So that means this is conservative. Okay, last one. ax plus ay. Ax plus ay over x squared plus y squared. Okay, all right, so let's take the partial of y with respect to x. Okay, so that would be only this part right here. So with respect to x, let's do the quotient rule. So the derivative of the numerator with respect to x would be 0 times the denominator minus the derivative of the denominator with respect to x, 2x, times the numerator, ay, divided by the denominator squared. Okay, so that's, I'll just leave it like that. Now let's take the partial with respect to y of the x component. So the x component is just this one right here. Okay, let's do the quotient rule again. So let's take the derivative of the numerator with respect to y, so that's 0, times the denominator, minus the derivative of the denominator with respect to y, so that's 2y, times the numerator, ax, divided by the denominator squared. Okay, so what do we got here? Minus 2xay minus 2yax. Okay, so they're the same, so this force is conservative. Okay, so that's how you check. Now, one more topic. Let's say you're given a potential energy. What's the conservative force associated with that potential energy? So if you have a force that's not conservative, there is no such thing as a potential energy associated with a non-conservative force. It has to be conservative for there even to be a potential energy associated with it. So if we're given a potential energy, what's the relationship between that and the conservative force? And the answer is, you take minus the gradient of potential energy. That's it. Minus the gradient of potential energy is the conservative force. Okay, and then how do you do a gradient? A gradient is just like three-dimensional derivative. So minus, just take the partial with respect to x, that's the I component, and then there's this minus sign, right? So the minus sign, the partial with respect to y, and that's the j component, and then the partial with respect to z, and that's the k component. Okay, so that's the relationship between potential energy U and conservative force F. And let's say it's one-dimensional, only in the x direction. Then these are gone, and you only have this. If we call that the L direction, then minus du dl would be the L component, and that's what we have here. Okay, so how do we use that? Let's try this example. So we're given this potential energy, and this particular one is saying the total energy at, so the total energy, total mechanical energy, kinetic plus potential, is 2 joules at x equals 0. And then it's not subject to any non-conservative forces. In other words, there's no work being done by a non-conservative force, which means energy is conserved, which means the energy is always 2 joules. Always. So the energy is 2 joules at any x. Right? It's 2 joules at any x. And then it's asking find the position where the kinetic energy is 0. So when the kinetic energy is 0, the total energy is still 2 joules. So let's find this situation. Okay, so potential energy is given 1/4 Cx4 equals 2 joules. Solve for x. So just move the 4 on this side. So x to the 4th equals 2 times 4 over c. 8 over c. And then c was given. It's 8. So this is 1. Okay, so x equals plus or minus 1. Okay, so that's part A. Part B, the forces. So that's where we need, how do you even get force from potential energy? And you take the gradient, which in this case, this one is one-dimensional. Okay, so to find the force, that conservative force associated with the potential energy, take minus the gradient, there's only the x component anyway, right? So take minus the derivative of 1/4 cx4. So then that's minus 4/4 cx3. So there, minus cx cubed. And then take this and plug it in right there. Okay, so that's it. All right, so again, I won't ask this on an exam, but give some of these problems a try. Hopefully it's not so bad. Let me know if you have questions about it, and then I'll see you in the next video.